During the previous test, some students have already discovered a problem. That is, when the camera rotates, the horizon will tilt. This is obviously unreasonable, so let's fix it together. To fix this problem, we must first understand the cause of this problem. Here I will simulate it for you to see if any students can figure out why. Let's first create a new plane. Pull it up to a certain position. You can imagine this plane as the camera's window. Remember this? Think of this plane as a window. When any edge of this rectangular plane is parallel to the ground, there will be no tilt of the ground plane in the window. On the contrary, if any edge intersects with the ground, the plane in the window will tilt. Next, we adjust the rotation angle of this plane to simulate edge, boosting the rotation angle of the camera. Press the E key, drag the arc, and adjust the plane rotation angle. Rotate left and right first, then rotate up and down. That is, rotate around the y-axis first, then rotate around the x-axis. You will find that this plane will always have an edge parallel to the ground. Therefore, in this case, the horizon in the captured image will not be tilted. Restore the rotation value of this plane to the initial value. Then, let's look at another situation. Press the E key and drag the arc to control the rotation of the plane. First rotate the camera up and down, then rotate the camera left and right. That is, rotate the camera around the x-axis first, and then rotate the camera around the y-axis. You will find that in this case, the edge of the rectangular plane will intersect with the ground. That is to say, the horizon in the window will be tilted. Why does this happen? Please note that the y-axis of the plane is always perpendicular to the plane. The reason why the horizon tilts during rotation is that when the camera rotates around the y-axis first, and then around the x-axis, the direction of the y-axis changes when the camera rotates around the y-axis, and it is not vertically upward. So, in essence, it can no longer be considered a left-right rotation. It can only be said that it is rotating around the y-axis in the inclined plane. In the strict sense of left-right rotation, it must be rotating around the vertical upward axis in the horizontal plane to be considered a left-right rotation. After such analysis, I think some students should understand. To make the ground plane in the picture taken by the camera not tilted, you must ensure that, when rotating around the y-axis, the y-axis is perpendicular to the ground plane. When rotating around the x-axis is parallel to the ground plane. How to achieve it? Here we provide a solution for you. Wrap the camera with 2 layers of parent nodes. When the outer parent node rotates around the y-axis, it is equivalent to controlling the camera to rotate left and right, because its y-axis can be kept vertically upward at this time. And no matter how the outer parent node rotates around the y-axis, the x-axis of its inner LD node is always parallel to the ground. Therefore, rotating the inner parent node around the x-axis is equivalent to controlling the camera to rotate up and down. Let's start the operation. Right-click into Blancroft the Arare window to create an empty node. Change phenodynamic. Remember that it controls camera axis, because in this game, the camera rotates around the basketball. That is to say, the center of rotation, when the camera rotates, is the basketball. So, we need to set the coordinates of the parent node that wraps the camera to be consistent with the initial coordinates of the Bull. Copy property value of transform component of basketball node. And paste itoth transform component of variety round node. Keep T position value, and set the rotation and scully value as of variety round to 0. Right-click the rotate roundy node to create an empty child node. Name it rotateroundx, which is used to adjust its rotation value around the x-axis. To control the camera to rotate up and down. Copy the original camera node. Hide the camera node and the plane node just now. Drag the resulting copy node to the rotateroundx node. Change the node name to camera. Associate its tracking object with the basketball node. At this point, we adjust the outer node rotateroundy to rotate around the y-axis. Adjust the inner node rotateroundy to rotate around the x-axis. Found that no matter how it is adjusted, the horizon always remains horizontal. The rest is to modify the code logic based on this. Now the rotation of the camera is controlled by adjusting the rotation value of the camera's parent node. So, we remove the control script on the camera node. Mount the camera control script to its parent node. Add member variable store record to parent node stack control rotation. Initialize their value as int the on start method. Then, modify the logic of camera rotation in the onLatUpdate method. Note that the rotation is based on the own coordinates as the reference system, so the last parameter should be set to true. Indicates rotation relative to the local coordinates. We should also record the shooting direction and angle. Save. Run and test. It is found that the camera rotates normally. No matter how it rotates, the horizon is always flat. However, there is a problem. If you rotate left and right for a certain angle and then shoot, the basketball will fly backwards. This is obviously wrong. We find the basketball control script. In the shooting control method, output the shooting angle and basketball speed. Save. Run. The test found that, when shooting straight ahead, the output shooting angle is 180 degrees. This is obviously wrong. The shooting angle should be 0 degrees at this time. Find the setting for shooting angle in the basketball control script. Check the relevant API again. Found that this property returns the rotation of the game object in world space expressed in Euler angles. Its value may be different from the rotation value in the inspector window. So here, we just subtract 180 degrees from the rotation angle. Remove the output statement in the basketball control script. Save. Run. The test found that the shooting direction is normal. However, the mathematical knowledge involved in the shooting logic. It may cause some confusion to some game enthusiasts. Discourage everyone's interest in game development. Of course, even if you don't understand trigonometric functions, there is still a solution here. Everyone sees this picture. You will find that the rotation of the camera after our modification is very similar to the rotation of the tank turret. The basketball is equivalent to the base of the tank turret. The camera is equivalent to the sight on the turret. Therefore, we can right-click on the rotatirunx node. Create a new empty child node, and name it muzzle. Indicates the direction of the muzzle. Adjust its position to be directly in front of the camera. From the top view, the muzzle, basketball, and camera are in a straight line. From the side view, they form a triangle. Because the rotation of the camera is now adjusted by the rotation of its parent node. No matter how it rotates, the relative position of the camera and the muzzle relative to the parent node rotatirundy remains unchanged. Therefore, we can get the world coordinates of the muzzle and the parent node rotatirundy during the program running. Then calculate the offset of the muzzle relative to the parent node rotatirundy. You can get the shooting direction. Then pass a shooting vector when shooting. Vectors have both size and direction. Both direction and force can be included in it. Based on this idea, we modify the shooting method in the basketball control script. Comment out the code for speed decomposition calculation. Change the parameter type of this shooting processing method to vector3. When adding force, you only need to pass this parameter. Is the logic instantly simpler and clearer? Then trace the code to find where this method is called. We use event subscription and publishing here. Finally, it is tracked to the throw controller script. The parameter value we want to pass here is a vector3. And this vector3 contains the force and shooting direction. The force is stored in the force variable in game data when the force is accumulated. The shooting direction should be calculated when the camera rotates and also stored in game data. Add a static variable throw vector3 in game data. And provide a static method to get the shooting settings. After the modification, In the shooting control script just now, you only need to pass game.as throw settings when issuing a shooting event. Finally, when the camera rotates, you need to record the shooting direction vector in the static variable throw vector 3 of game.as. Open the camera control script. First, add the muzzle node member variable. Initialize its value in the onStart method. Then, write a method to calculate the shooting direction. The shooting direction is actually the muzzle world coordinate minus the current node's world coordinate. The last step is to update the value of the shooting direction vector in real time, in the onLatUpdate method in the camera control script. Save. Run and test. I found that a little bit of force can throw the basketball very high and far. This is what I expected. There are two ways to deal with it here. One is to use the method we talked about in the previous course to readjust the force. The other is to keep the force unchanged and readjust the initial position of the muzzle. Just pull the muzzle closer to the original coordinates of T. He parent node. Here I will analyze it according to my previous code logic. It was found that the force was the force B4, and the shooting direction was a unit vector with a modulus of 1. Based on this, we can try to make the modulus of the local coordinate vector of the muzzle also 1. Then the default shooting direction is 45 degrees. So, in the onStart method of the camera control script, I added a line of code to initialize the local coordinates of the muzzle. Set its x-coordinate to 0, and tilt it up 45 degrees in the YZ plane. Save. Run and test. Shoot at the side of the basket. The force and angle can ensure a goal. In the longest distance shooting in the basketball court, the strength and angle can also ensure the goal. However, I found a bug when preparing for the class. It is when shooting from a very long distance. The total score of a goal should be increased by 5 points. In fact, it increased by 10 points. It means that the method of accumulating points for a goal was executed twice. Let's track the code. Open the basketball control script. In versus code, press the shortcut key Ctrl plus Shift plus O and enter on trigger. Find the method called by the trigger. Further, find the method of scoring judgment. After careful thinking, we found the problem. During the flight, as long as the basketball collides with the trigger, a score judgment will be made. Therefore, when the basketball bounces in the net and hits the trigger in the net again, or when the basketball bounces from the ground and hits the trigger again, a score judgment will also be made. Therefore, multiple score accumulations will be performed. And if it bounces from the ground, the trigger of the camera on the backboard may be obtained when calculating the score. Therefore, in the first step, we move the method of whether to score a goal to the inside of the upper branch. When the basketball collides with the trigger in the net, it is judged whether to score a goal. After this change, the problem of multiple scoring can actually be solved. Because even if the basketball hits the goal and bounces off the ground and hits the trigger in the net, the name of the trigger has been recorded in the trigger array at this time. And it will not be added repeatedly, so it will not be judged repeatedly whether it is scored. And when calculating the score, the collider obtained must be the collider in the net. There will be no problem with distance calculation, and there will be no problem with single score calculation. If there are still students who are not assured, you can also use the method we talked about before, which is to make the audience sound effect play only once during a shot. We will not waste your time here. Save. Run and test. Focus on testing whether the ultra-long distance shot basketball will be scored repeatedly when it hits the ground and bounces. After testing, all functions are basically normal.